Welcome to our deep dive into the fascinating world of sharks and their incredible adaptations for deep-sea hunting. Today, we'll uncover the secrets behind how sharks manage to stay underwater for so long without lungs. Join me as we venture into the twilight zone where sunlight fades and the pressure mounts, to witness the remarkable adaptations that allow sharks to thrive in the deep. The deep ocean presents a formidable challenge for any air-breathing creature. Yet, sharks, masters of their domain, have evolved a remarkable solution to the problem of oxygen. Unlike us land dwellers who rely on lungs, sharks have developed an ingenious way to store and utilize oxygen directly from the water, their blood and muscles. Crucial to this adaptation is a protein we're all familiar with: hemoglobin. This molecule, found within red blood cells, acts as a sort of molecular taxi service, picking up oxygen from the gills and ferrying it throughout the shark's body. But sharks have an additional secret weapon: myoglobin. This protein, residing within muscle tissue, acts as a local oxygen reserve, much like a scuba diver's backup tank. Myoglobin binds oxygen even more tightly than hemoglobin, holding onto this precious resource until it's desperately needed. This allows sharks to withstand periods of intense activity, like chasing down prey, without needing to surface for air. Imagine having your own internal oxygen reservoir, allowing you to hold your breath for minutes, even hours on end. This remarkable adaptation is particularly vital for deep-diving sharks. As they descend into the abyss, the pressure increases dramatically, squeezing the oxygen out of their blood. But thanks to myoglobin, their muscles remain oxygenated, allowing them to function even in these extreme conditions. The combination of hemoglobin and myoglobin grants sharks an extraordinary level of underwater endurance. Consider the oceanic white-tip shark, a formidable predator known for its long-distance migrations across vast stretches of open ocean. These incredible creatures can remain submerged for hours, their muscles fueled by the oxygen reserves stored within. And then there's the great white shark, an apex predator that needs no introduction. Their ability to launch themselves out of the water in pursuit of prey is a sight to behold, a testament to the power and efficiency of their oxygen utilization. In the next chapter, we'll delve deeper into the world of deep-sea sharks, exploring how they manage to conserve energy and oxygen in an environment where every movement counts. As we descend further into the ocean depths, we enter a realm of perpetual twilight, a place where food is scarce and energy conservation is paramount. Here in this cold and unforgiving environment live the true masters of deep-sea survival. Sharks like the Greenland shark and the bluntnose sixgill shark. These ancient mariners have mastered the art of slow living, their bodies finely tuned to extract every last ounce of energy from their surroundings. Their secret? A remarkable ability to slow down their metabolism, reducing their energy demands to a mere whisper. Imagine a world where your heart beats only a handful of times per minute, where your every breath is measured in minutes rather than seconds. This is the reality for deep-sea sharks. Their slow metabolic rate allows them to conserve precious oxygen, stretching their limited reserves over astonishing periods. The Greenland shark, a creature that can live for centuries, embodies this slow and steady approach to life. Its movements are deliberate, almost languid, as if it exists in a state of perpetual meditation. This unhurried pace of life allows it to survive in the depths where food is scarce and every calorie counts. The bluntnose sixgill shark, another denizen of the deep, employs a similar strategy. Its large, bulky body and sluggish movements are a testament to its energy-efficient lifestyle. This ancient species, a relic of a bygone era, reminds us that in the deep ocean, slow and steady often wins the race. But how do these sharks achieve such a low metabolic rate? The answer lies in their unique physiology. Their cold-blooded nature allows them to match their body temperature to their surroundings, reducing the energy expenditure associated with maintaining a constant internal temperature. Furthermore, deep-sea sharks have evolved specialized enzymes that function optimally at low temperatures and high pressures. These enzymes, essential for basic metabolic processes, operate at a slower pace, contributing to the shark's overall reduced energy demands. This remarkable adaptation, however, comes at a cost. The slow metabolic rate of deep-sea sharks limits their ability to recover quickly from strenuous activity. In the next chapter, we'll explore another fascinating adaptation that allows sharks to conserve energy in the deep ocean. Their unique approach to buoyancy control. In the weightless embrace of the deep ocean, where even the slightest expenditure of energy can impact survival, sharks have evolved a remarkable adaptation buoyancy control without the need for constant swimming. Unlike bony fish that rely on gas-filled swim bladders, sharks have turned to a rather surprising organ for buoyancy: their liver. Imagine an organ so large, so rich in oil, that it acts like a natural flotation device. This is the reality for sharks. Their livers, often constituting up to a quarter of their body weight, are filled with low-density oils, primarily squalene, which is significantly lighter than water. This oily secret provides sharks with a natural buoyancy, counteracting their heavy skeletons and allowing them to maintain their position in the water column with minimal effort. It's like having a built-in life vest, allowing them to conserve energy that would otherwise be spent fighting to stay afloat. By adjusting the amount of oil in their liver, sharks can fine-tune their buoyancy, ascending, descending, or hovering at a specific depth with remarkable precision. This ability is crucial for deep-sea sharks, allowing them to exploit different depths and prey without wasting precious energy on constant swimming. Consider the deep-sea cat shark, a small, stealthy predator that lurks on the seabed, patiently waiting for unsuspecting prey. Its large liver, rich in low-density oils, allows it to hover effortlessly just above the bottom, conserving energy as it lies in wait. Or picture the frilled shark, an ancient species with a serpentine body and needle-like teeth. Its elongated liver, extending for almost half its body length, provides the buoyancy it needs to navigate the depths with minimal effort, its sinuous movements a testament to its mastery of buoyancy control. This remarkable adaptation, however, is not without its drawbacks. The oil-filled liver, while providing buoyancy, also makes sharks vulnerable to temperature changes. Unlike bony fish, which can regulate their internal temperature, sharks are cold-blooded, their body temperature fluctuating with their surroundings. In the next chapter, we'll delve into another fascinating aspect of shark physiology, exploring how they manage to conserve oxygen during deep dives by selectively regulating their gill function. In the depths of the ocean, where oxygen is a precious commodity, sharks have evolved a remarkable adaptation to conserve this life-giving gas-selective gill function. This ingenious strategy allows them to regulate the flow of oxygen across their gills, maximizing efficiency and extending their dive times. Imagine being able to control the amount of air you breathe, taking in only what you need, when you need it. This is the reality for sharks. Their gills, those feathery organs responsible for extracting oxygen from the water, are not always operating at full capacity. During deep dives, when oxygen conservation becomes paramount, some sharks can partially close off their gill slits, reducing the flow of water over their gills. This seemingly counterintuitive action actually helps to conserve oxygen. By limiting the amount of water passing over their gills, sharks reduce the surface area available for gas exchange. This slows down the rate of oxygen uptake, but also minimizes the loss of precious oxygen from their bloodstream back into the water. This delicate balance between oxygen uptake and retention is crucial for deep diving sharks. Consider the Portuguese dogfish, a small deep-sea shark known for its ability to tolerate low oxygen levels. During deep dives, this remarkable creature can reduce its gill surface area by up to 80%, significantly extending its dive time. Or picture the goblin shark, a bizarre-looking creature with an elongated snout and retractable jaws. This deep-sea dweller is thought to employ selective gill function to survive in oxygen-poor environments, its unusual appearance a testament to the extreme adaptations required for deep-sea survival. This ability to regulate gill function is just one example of the many physiological adaptations that allow sharks to thrive in the deep. It's a testament to their evolutionary success, showcasing their mastery of underwater breathing techniques. But selective gill function is not without its limitations. While it allows sharks to conserve oxygen during deep dives, it also reduces their ability to expel carbon dioxide, a waste product of metabolism. In the grand tapestry of life, sharks stand out as masters of adaptation, their physiology a testament to the power of natural selection. And there you have it, the incredible adaptations that allow sharks to thrive in the deep sea. From storing oxygen in their blood and muscles to slowing their metabolism, controlling buoyancy with their livers, and even regulating their gill function, these ancient predators have evolved a suite of remarkable strategies to conquer the challenges of a world without air. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating insights into the natural world. Would you like to learn more about how sharks thrive in extreme environments? Let us know in the comments below.